planes flying through the air, submarines gliding through the ocean a quarter-mile deep. Some of the most impressive feats of engineering we see today are dependent on properly estimating the complexities of drag force on moving objects. To do this, engineers use the drag equation to simplify object shape, fluid flow properties, and attack angle into one easy-to-use drag coefficient.
And that's where the coefficient of drag comes in. Coefficient of drag is a ratio between the force felt by the object and the force provided by the dynamic pressure. However, the coefficient of drag can also be dependent on the Reynolds number, which is why we incorporated that into our project. The Reynolds number is a dimensionless quantity that characterizes the flow around an object.
And that brings us to our project, where you have something super complex like a rocket engine turbopump. You really want to know what all the different forces are at play. So to find the drag force on our particular turbine here, and that's right, turbine, not turbine, we actually need a controlled environment in order to figure that out. So that brings us to our wind tunnel. So as you can see, the fan on this side pulls in air through our controlled wind tunnel environment. It comes straight through our straightening section on this side, which basically has a bunch of little passages to have laminar flow come through and then shrink down to our particular test section over here, where we have our actual fin, our turbine fin sitting here ready to be measured. And then it comes through here and then exhausts through the back over here. And just to talk a little bit about our sensors here, Brydon here to explain what's going on.
Yep, so as you guys remember from that drag force equation, there were several physical things that we needed to measure. The first being pressure. So we just have the barometer on Nick's phone to measure pressure. This is gonna stay pretty constant as we're in the same location. The next thing we have to measure is the temperature of the wind inside the wind tunnel to help us get a better number for our air density. So we have a thermistor down here, a thermal resistor, and that's wired through an Arduino, and you can see the output coming on Nick's computer. Our next sensor is this load cell. So if you zoom in on this is how we're measuring the force of drag, and we're actually measuring it indirectly through this lever arm, and that accomplishes two things for us. First, it gets the force sensor out of the wind tunnel so that it doesn't affect our aerodynamic profile. And it also, as the sides of that lever arm are uneven, we get an amplification ratio of about 8.5 for this situation. And that amplification ratio takes the force that is felt by the fin, which is relatively small, and amplifies it to something that the force sensor is more able to read. And you can see the output of that force sensor. It's pretty small right now, or it looks like it's pretty noisy, but if you take it off back to zero and reapply the load, you can see we're actually getting really good data, and it's a very constant drag force that we're reading. Now to talk a little bit about how we selected and calibrated the main three sensors of our system, excluding the barometer, as that was pretty simple. The main three sensors, the thermistor, an airspeed sensor, and a load cell, they all had very different stories on how we calibrated and selected those sensors to be a part of our final system. So we'll go into that now.
We chose the thermistor because we had experience with it, it had a low uncertainty, and it was incredibly easy to calibrate. In order to calibrate it, we simply choose a temperature that we know is to be true. For our example, we used an ice bath that we assumed to be 0 degrees Celsius. We put the thermistor into the ice bath, measured the bias that it was receiving at that 0 degrees Celsius, and then took that off from the temperature that it was measuring.
So compared to our thermistor setup, we actually had quite a few problems with our load cell and iterating to get it right. To start off with, we had initially wanted to use a force sensing resistor to measure our force, but we ended up not being able to get any reliable data for that. So then we went to this load cell, but then we weren't able to get this one to work either. So we went back to one that we had experience with from class, but then that one had a little bit too high of a range. So we eventually were able to get this load cell to work, which is great for us. It has good uncertainty and has a capacity of 10 kilograms, which is right around in the range that we're trying to measure. So to calibrate it, we actually did two different calibrations. I have one of them set up here. In the first calibration, we just applied weight directly to the load cell. And then in this setup, we actually used our force amplifying lever arm to apply load to the load cell. So you can see right now we have it zeroed out. And then if I apply weight, it goes up to a higher reading as it's bending our load cell. And doing this calibration this way allows us to ensure that what we're assuming about our force amplification in this lever arm is actually correct. So I measured out exactly a 6-to-1 ratio in our lever arm, and going through our data between applying the load directly to the load cell and applying it through this lever arm, we were within 4% of accuracy, which was pretty good for us considering that it's really hard to get the measurement exactly right. So doing our calibration this way allowed us to reduce the amount of assumptions we were making and have higher confidence that our calibration, which is what we used to determine what output corresponds to what level of force. So doing it this way really allowed us to have a lot of confidence in our method.
The story with our velocity sensor was quite a mess. It was very different here. So our original sensor was this guy. It was a little DP sensor connected to a pitot tube, which basically measured the difference in our stagnation pressure and our static pressure and gave us basically our dynamic pressure and our velocity. So actually, we got rid of this because it had a bunch of problems with its digital readings. But what we used instead was just the calibration from the actual wind tunnel itself. So there were calibrated values from a while ago that basically allowed us to determine what the actual velocity in this was as a function of the frequency in here. So that calibration was pretty similar. Again, it used basically a pressure sensor in here to basically find the velocity in the same way. When it's at essentially zero, you have nothing flowing through, you know that it has to be reading zero velocity, so you can sort of get rid of that same bias that way.
So as you can see here, this is our individual trial data. First is the output from the force sensor. Here is an example of the measurement from the barometer sensor. Now you can see the temperature sensor's results. And all of that really comes together to give us our resulting coefficient of drag. And we also plotted the coefficient of drag against the Reynolds number, which really solidifies the difference in both wind velocity and the geometry and how they impact the coefficient of drag.
And so it's great that we got nice results from something like that. But really, we did have some sort of inaccuracy with that, or sort of uncertainty of our results. So sort of with our CD, we had a relative uncertainty of 3.5%, and that mostly came from our force sensor. Its uncertainty was the highest from our change. And then from the velocity, we actually had a much lower uncertainty than what we initially had anticipated prior to our switch. And then for the Reynolds number, we had less than 1% relative uncertainty, which is pretty good, which mostly came from the length of this actual fin. So moving on to sort of the improvements in error from what we had, you recall that sensor that we got rid of, the digital differential pressure sensor. This is sort of an example of the data that we got from it, which essentially had a problem in magnitude and a problem in frequency at sort of those higher modes. And so that kind of just told us something about digital sensors, which is that that really can be sort of errors with sampling rate and all these other things that would really just be fixed by using something analog, kind of like that.
Yeah, and that was actually one of the biggest things that we concluded from this experiment. If we were going to go back, we would definitely use a differential pressure gauge, something actually similar to what you see on the screen right now. Even using an analog measurement that you visually collect with your eyes, just measuring between the two different tick marks right here, even something like that would be more accurate than the measurements we were getting from the digital differential pressure sensor.